Hello. So am I audible? You can type in the chat box if I'm audible. Okay. So I'll just share my screen. Okay. I hope it's visible. So my screen is visible, right? Yes. Okay. Thank you. Mm, Okay. So we'll just wait for a couple of minutes and then. Okay. So just type in the chat box if there is any issue or any doubts you have. Uh, yeah. Just a second. So yes. So how many are there? Yes. Okay, so now there are one, two, three, four, five, six people. Cool. Mm, yeah. So I'll just wait one more minute, and then we'll start. Okay. So I think we'll start. It's six. Okay. So yeah. Okay. So good evening, all. Yes, sir.
We can do a quick intro of
Yes, sir.
all the people, why they are here, where they are from, what do they expect out of these sessions, and all that.
Yes, sir.
We can make
So
a note of all those things, and so so that the future sessions you can schedule or you can tune as per their requirements. So before you start solving problems or dumping your information, let's can do a quick intro to them, especially the one who are coming from the NPTEL registration. So just have a formal, like an informal chat, and then for 15 minutes, take down notes, and then you can get started with maybe actual problem solving.
yes. So shall I just ask them to unmute one by one. I think that's
Yeah,
better
yeah.
because there
Just
are
have
many.
a friendly chat. I think don't be so formal of hand, raise your hand and all that. There are not too many people, right? There are like 8 or 9 people. So
Yes.
so just have a
I'll
catch
just
with them, and then
yes.
I'll join again after a while.
Okay, sir.
Okay.
Yes.
Yeah.
Yes. Okay. So I'll just stop sharing for a while and introduce myself first. So hope you can see me. So I'm Karthik. I'm working under Ramakrishna sir in the Department of Electrical Engineering. I'll be the TA for Linear Systems Theory. So this is actually the same course run here this time. Uh, yeah, and we'll meet regularly in the evenings, 6 to 7 Tuesdays. So yeah, you can be like free to ask all your doubts in that week which you had. I think the week one is the officially it's over, and assignment two has. I mean, the week two has started. So you can ask today. You can ask anything related to week one. It's okay if you have watched week two also. You can ask those doubts. So yeah, you can start introducing yourself. I'll just yes. So yeah, you can start introducing yourself. I'll just okay. Yeah, first would be Arjun. So so you can unmute and just say why here. Things like that. Arjun, are you here?
Hello, Karthik. I'm
Yes,
audible.
yes, yes.
Yeah, I'm Arjun Busal. I'm doing this course at the college also.
Okay,
I'm here to just uh, clear my doubts. If,
but why linear system theory?
I wanted to take more course on control theory, and this seems to be the foundations for other advanced courses.
Good. Okay. Okay. Now, Srijan, are you here? I think you just joined right now. Srijan, you can unmute yourself and just introduce and why you took this course, etc. Okay, I think Srijan is not here. Okay, so we'll move on to Karnan.
Yes, sir. I'm audible.
Yep. Yes.
So I am Karnan from Kandigram Luda Institute, Tamil
Okay.
Nadu. Actually, I
Okay.
am
Yeah.
doing PhD in control theory.
Oh, nice.
Uh,
Cool.
for the basic, I need this course.
Okay.
Uh, Actually, I'm in mathematics department. We are understand the mathematical part, but we are not that much knowledge in the circuit theory. If you
Mm-hmm.
while seeing the first week course, I bit not understand the circuit theory concept.
Ah,
If you clear that too the our mathematical department and other department also
yeah.
it
So
is.
today we'll be doing one problem on DC motor. So we'll model a state space DC motor today. So you'll understand both
Okay.
electrical as well as mechanical system.
Okay. Actually, we are not that much knowledge in that field. That is why I'm asking this one.
Yeah. Got it. Nice.
Thank you,
So
sir.
next would be uh, Pugendi. Pugendi is not.
Yeah,
Yes.
yeah.
Yes. Yes.
Is that audible, sir?
Yep.
Yeah, sir. Yeah, I'm registered for this course. Actually, I'm working as an associate professor in a self-financing institution in Tamil Nadu, engineering. Probably basically I'm an electrical engineer, and I've already attended control engineering course taught by Professor Ramakrishna already, and I have a few uh, uh, lectures I have listened in nonlinear control
Hmm.
also. And just to brush up the basics regarding linear systems, I'm just looking for new ideas, maybe new problems. Always, professor, choose new set of problems
Yes.
in each. Even if I register for next time for linear control system theory, I can find a new set of problems. So to get that also and brush up the basics, I'm here for that. Yes.
So you are from you're teaching electrical. So
Yeah, yeah. I'm an UG electrical and PG process control and instrumentation,
so
and I'm
it's
interested
so like
in, yeah,
continue. Sorry. Yeah.
yeah. I'm interested in the control. I'm just at the verge of completing my research in process control also. So getting out the basics correctly and finding out new set of problems from professor. I'm eager to join this
Yes.
course.
Yes.
Thank
So
you very
like
much.
since you are in the teaching, I think you can explain to Karnan what he just asked about electrical. So even during the tutorials, like if I make a mistake, you should point it out. I mean, all of you. So
Yes,
yes,
obviously.
yes. So because anyone can make a mistake. So just point it out. It doesn't matter. So yeah.
Yeah, thank you
Okay.
very much.
Cool. Next would be Subro Banerjee. So if you can unmute and just introduce yourself.
Hello,
Yep.
am I audible? Yeah,
Yes.
so actually I'm taking the dynamical system course. So as a revision, I am taking this course. So that's why I'm from
Okay.
aerospace department, PhD student. Yeah.
Nice. Nice. Okay. Siddhant, can you introduce yourself? Siddhant. Just,
Hi, I'm audible.
yeah.
So right now I'm working in Bajaj Auto. So I just joined. So I have
Mm-hmm.
completed my MTech and I am in motor control team. I just wanted to widen my knowledge about control. So I thought of studying it for advanced control system. I thought this course will be provide me good basics for that.
Yeah. Okay. So that's nice. Soumyadeep. Soumyadeep. Here. Mm, okay. Yeah. Cool. So okay, I think he's not here. Okay. Anyways, so we'll just. I think I know the others because I've interacted with them. So it's fine. So we'll just move on without wasting much time to the content. Uh, okay, one sec. I'll just share my screen. Okay, so my screen is visible, I guess. So anyone can unmute and just tell me if the screen is visible.
Yes, sir, you are yes.
Cool, thanks. So firstly, I hope you have gone through week one lectures, which deals with uh, system modeling, right? So why do we need a model, and like what's the use of a model? So essentially, uh, for controls, for model based controls to work, not the learning based, where you have the new learning machine learning techniques to deal with control, developing controls even without a model. So we'll just set that aside. The traditional all control techniques need a model, so at least a sound enough model. For example, you might have seen the model of a client web server in the tutorial. The For example, the pendulum, of course, that's the the prime example in control theory. So yeah, so today, so if you have any doubts regarding the week lectures, just either you can, what do you prefer, before the class or after, during the end? So someone can unmute and say, before, or before we start the tutorial problem, or after. Anyone can say. Hello,
Yes,
am
you
I
are audible.
audible? Okay.
Yes, you are.
So yeah, what do you prefer? The doubts regarding the weeks.
I think after will be better.
Cool. Okay.
After, yeah,
So
yeah.
I take that as the decision for all. Okay. So cool. So we'll start off with a simple electromechanical system, your DC motor, which I think everyone in who deal with physical system may have to use it somewhere or the other. So we have a equivalent circuit. So I am not saying how this equivalent circuit has come, because it comes from the first principles, like what a resistor, how the windings are there, the inductance, things like that. So that I'll have to take you to the, okay, someone's here. One sec. Okay, admit. Cool. Okay. So that I'll have to take you to the, basics of electromagnetism and things like that. So I'm just assuming we have a voltage input here, and this is the resistance of the winding, the armature winding, and there is a field winding. So I'm just using a armature controlled DC motor. So you can stop me anywhere if you have a doubt. So this is the inductor. So for mechanical people, it would be, corresponding to your flywheel, and this is the current through the inductor. Then we have something called as a back EMF generated due to the conductor, cutting the flux lines of the field winding. So that's how a DC motor actually works. So there is a huge, subject for DC machines. So you can look at that if you want. And then we have a shaft to which a load is connected, and it rotates at theta. So this is the mechanical side of things, and this is the electrical side of things. So basically, the control objective is to control the theta or theta dot, which is your angular velocity of the load, using an input voltage V. So the system has some dynamics, right? So we need to model that first. So for physical systems like this, we usually go to the first principles. So which means first principles in electrical would mean Kirchhoff law, the voltage current law, the Ohm's law, and things like that. In the mechanical side, it's just your Newton's equations. So those are like equivalent things, in both the domains. So for physical systems like this, it is easy to model comparatively compared to, say, your web client server, where you don't have any physical laws governing. It would be just flow of mass or things like that. So it's very difficult to model such systems. So here, I think the electrical people can relate to this. So V will be equal to, so all these small v and I are all functions of time. Okay. IR plus L di by dt plus the back EMF. So okay. So with regards to electromagnetic induction, we can say the back EMF is proportional to the rotational velocity. So this is basic 12 standard physics, right? So it is proportional to some the velocity at which the motor is rotating. So that is k1 theta dot. Omega is theta dot. And in the mechanical side, we have the torque. So the motor generates some torque, which will be equal to the moment of inertia J times theta double dot. Okay, sorry for using two notations. So di by dt, okay, I'll just use it here as well. So this will be t square theta by dt square, plus there will be some friction, right? So friction would be dependent, the loss due to friction would be dependent on the velocity. I'm not assuming any spring or any external loads right now. It's unloaded. So this is the system dynamics on both the sides. So this you can arrive from the first principles. Now, how do we model this as a linear state space system? So for that, okay, there is another one. So tau, the generated torque, again, class 12, is proportional to the current through the inductor, right? Or the current through the winding. So okay, again, someone's here. I'll admit. So how do you model this using state space? So a state represents an energy storing element, right? So in this, how can someone answer how many energy storing elements are here? Anyone can unmute, free. You're free to unmute and say how many energy storing elements are here. Anyone? Or
one maybe.
Just one.
One is an electrical parameter and the other one is a mechanical parameter.
Yeah, so how many in the electrical?
Electrical, we have I current di by dt. One.
Yes. So the element is the inductor.
Yeah, inductor is there. And
okay.
In mechanical, you have a square there, so probably we can have 2.
Correct. Correct. So there are 3 elements. So you need the system order would be a third order system, right? So that's even in your classic control theory, the number of poles, would be the if there are 3 storing elements, it will be a third order polynomial. So in the same way there are 3 states. So if I take this my first state, now we know that state space is not a unique representation, so I can take x1 as theta, x2 as theta dot, and and x3 as the current through the inductor. So what can I directly say from this definition? X1 dot is x2, right? So x1 dot is x2 because it's just the derivative. The first derivative of angular position is the angular velocity. So you get your first equation directly. Now what about x2 dot? X2 dot is nothing but theta double dot, right? So you can take this equation, I'll just call it B, and this equation as A. So you can directly, just swap the terms here and there, and then you can rewrite this as minus tau by j. Okay, it's plus tau by j minus b by j d theta by dt, right? Okay, but we need everything in terms of x1, x2, and x3. So what is that? So tau can be returned as proportional to the current. So that will be K2 times the current. What current is taken as x3. x3 by j minus b by j. D theta by dt is nothing but x2. Cool. So we have our second equation. So is everyone with me? Like, any doubts still here? Okay. Cool. So you have 2 equations. You need one more. So that's pretty straightforward. So x3 dot is nothing but di by dt from this. So x3 dot is di by dt. So from equation A, you can use the similar way that you use for the mechanical side. So that will be V by L minus, minus I times R by L. Again, okay, sorry for that, minus E. So again, I'll substitute what E is. So I'll get minus I is x3 R by L minus E is nothing but K1 theta dot. And theta dot was x2. So that is, okay, I think it was K2. Okay, it was K1. Yeah. K1 theta dot, which is x2 plus V is your input. So I'll just write it as V itself here. Usually the notation is U, or in A plus BU, things like that. So yeah. So you have your third equation here, x3 dot. Correct? And say now I need to control the position. So you generally measure the position output of the motor. So you take the output y equal to theta, which in this case is x1, I hope. Yes, it's x1. So you have your output equation. So you can just write x1 dot in a matrix form, right? Because it's all linear now. If you see, so this will be nothing but something times x1, x2, x3 plus something times v. So can anyone say the first row of the matrix? Unmute and say the first row of the matrix.
0 1
dot.
0.
Yes.
0 1 0.
0 1 0, right?
Correct.
Yes. And the second, someone else can say maybe. So
0
you can look at
minus
this
b by
equation.
j, K2 by j.
0 minus b by j, K2 by j. Yes. And the third from this equation, someone else can say.
0 minus K1
Minus K1
minus R by L.
I think there should be by L also, I feel. So yes, there should be an L. Yeah, there should be. Yeah. Okay. minus,
RPM.
yes. And what about the
And
B
the
matrix?
constant 1 by.
No, this matrix, I mean.
Yeah, 0, 0, 1 by.
0, 0, 1 by n. Yes. And y equal to the C matrix
Equal to
times x1, x2, x3.
1 0 0.
1 0 0.
Cool. So that's it, right? You just modeled the DC motor. Now you can use this to control the position or the speed, or So so that we'll see later. How do you, if it is even controllable, or if you can even make it track something, or so that we'll see in the later. So this is just the modeling part. So is anyone like has any doubts regarding this? How you got, so this basically I wanted to show how electrical and mechanical, some two different domains can be modeled, simply using linear method. So like, I mean, into a linear model. So is anyone has any doubts or anything you want to add, like how, you know like you can just add into the knowledge, if if anyone has any. Okay, cool.
Can you explain how we took Y?
Okay, how we took y. So that depends on your goal and your sensor actually. So assume I have a speed sensor, I don't have a position sensor. Okay, so what would be my y matrix? It
0
would
1
be
0.
0 1 0, right? I mean C matrix, sorry.
Yes. Means here we are intending to control the position.
No, it's actually more of the sensor, even if we have the intent to control the position, there is something called the observability of the system. Can we find the position from the velocity, or can you find x3 from the sensor measurement you have? Got it. So it depends on how your sensors are placed. So if you have sensors for all three, x1, x2 and x3, you have a current sensor, you have a position sensor, you have a velocity sensor, then your C matrix would be I, right? The identity matrix, because you can measure all three. So C matrix generally shows how your sensors are placed. Similarly, the B matrix shows how your actuators are placed. So you can connect it to the physical, system actually. So your B
C
matrix actually
matrix, how can it be an identity matrix?
the C matrix, you mean?
If we connect all
So
the three.
yes. So I have, so y, so I have y1, y2, and y3 as my sensor measurements. So
Okay.
that will be 10000100001 times x1, x2, x3. Yeah. If all the sensor measurements are directly available, like you can place all, a sensor for each state, then you can
Okay.
have this, right?
So basically, to control the shaft, what all sensors do we require? Control the say velocity of the shaft, angular
Hmm.
velocity.
So you need to control theta dot, say to some 5000 rpm, for
Yeah.
example. So do you actually need the position? Like we'll see in there are like pole placement things, and like where we need all the states, you know, where we need all theta dot and I. So there is a technique called pole placement. So yeah, we'll see that in the later lectures, if we actually need all the states, or I mean, if we need so many sensors, or we can estimate states from sensors, sensor data, things like that.
Okay. So we are building a closed loop system, right here.
Exactly, that's the final goal. So
Hi, you mentioned about the B matrix that will
yeah.
control. You said it will control the actuator. How can you please explain more on that?
So
Actuator.
yeah, so here the B matrix shows how the input enters the system, right? So how it enters, in the sense how the actuators are placed. So here there is only one actuator, which is your voltage source for the motor. So this is your voltage source. It's a variable source. So for your speed control. So that's actually your actuator, right? For a robotic arm, it will be a
Okay.
it yeah. So So it depends on how many motors you have in the robotic arm. So I hope it's clear. So your B matrix would be different. Okay, for I'll give an example of uh, a glider system or a plane. You have more than two. I'm just using the basic one, where one is the thrust and other one is the pitch angle, right? So you can control both. I mean, that's the most basic one. You'll have other controls. So there are two actuators, and then you have two inputs, right? So that B matrix shows actually how the input enters into the system. So 1 by L is actually your gain, right? 1 by L is actually a gain.
Yeah.
Yeah. So if you give some 5 volts here, it will be 5 by L that actually enters the system. Correct.
Yes.
Yeah. So that's how.
And in all the literature, we also have on D. What is the
Yes.
significance practical?
So D is actually something called your feed forward term. So I think we'll cover that, but mostly we don't have such terms for your classic control. We don't. Uh, I mean, there are techniques which use feed forward techniques. So feed forward in the sense how the input directly enters the output. So there will be some D times U. So which means if you have seen your block diagram, so you have a plant. Oh, I mean, okay. Then you have a controller. Then you have your output of the plant. You have sensor measurement with all the noise and things like that. And then you have your okay. So if this doesn't have any feed forward, so this is only feedback. So output is directly fed back, right? But you can sometimes have something called as a feed forward term. So feed forward term actually is a bit tricky because it actually requires all the signals to be known beforehand. Okay, we won't get into all that.
This is
Feedback is
like bypassing all the compensators and stuff.
it's not bypassing. It's actually there'll be some gain here, and so like it's not bypassing. It's just adding to the sensor measurements directly. The output, it's just an addition to the output, right?
Understood. Where such a system is used?
I
Is there any
think,
practical?
yeah, for precision tracking and things like that. So the main problem. Okay, we'll study. Not in this course, but there are problems tracking where you can't have precision tracking. For a lot of mm, practical systems, you need precision tracking where where we know what it's to be tracked and things like that. But usually it's for precision tracking and stuff.
Okay.
Good. So I'll just, yeah, any other doubts regarding this? Okay, or else we'll move on to the next problem. So yeah, so so we'll do a small face portrait problem, which is very easy. Like a small two-dimensional system. Just to understand what face portraits are. So does have everyone gone through the face portrait thing in the handout in the lectures? I hope everyone has. Okay. So we have, or I'll take an example. X1 dot is x2 minus x1, and x2 dot is x1 minus x2. Okay. So what are face portraits? So can anyone explain, what are face portraits or what your understanding of face portraits are? Anyone can unmute. Okay.
They're basically the plot between
Plot between.
two states.
Okay. So it will be x1 and x2. Correct. So what plot? What is it plotting?
The function that relates both x1 and x2.
A function. So that will be just x1, say x1 equal to x2 square, right? That's not what we are plotting, right?
The rate of change.
Okay, you're closer. So I think field theory, electrical people and fluid mechanics people will know what exactly it is. So in electrical, there is something called electromagnetic field theory. And in fluid mechanics also, you have these things. So both electrical and mechanical people would know. Okay, anyways, so what you actually plot is at each point on this plot. I'm not plotting for this one. So at each point on the plot, it shows in which direction.
Somebody raised hand.
Okay, okay. Okay. So
Swati raised hand.
yes, Swati, yeah, you can unmute and say it. It's okay. You don't have to raise hands. Okay, I think it's by mistake or yeah. Yes. So it actually shows the how the dynamics would evolve in the next instant. Whether it will go this way or this way or this way. It gives a plot of how the dynamics would change in the next instant. So it actually gives a lot of visual intuition on how the system is. Later on, we'll see that for some systems, we can't even solve for x1 dot and x2 dot. We can't solve differential equations. But phase portraits gives you an understanding of where the system would land up, things like that. Okay, so for this one, we'll just start. The you can't do this for all complex systems and things. For simple system, you can hand draw. For other complex systems, you can always use MATLAB and Quiver plot. So you can look that up. Quiver function on MATLAB. So you can use that to plot vector fields. Okay, so I haven't used the term yet, so it's called vector field. So yeah. Okay, so can anyone tell me what the vector field or what the arrows, the direction of arrows would look at x2 equal to 0 or your x-axis? Anyone can unmute, can say, put x2 equal to 0, so x1 dot would be, anyone can say, either like everyone has understood or no one has understood anything. So
Towards the negative real axis.
okay, so okay, wait one second. Towards the negative real axis.
It's not a real axis anyway. I mean, towards the left.
Why is it only towards the left? That is only the one component, right?
Okay,
That's only the first component. What about the second? So yeah, for x1 dot, it is towards this, correct. But for what about the other component, x2 dot? What about the motion in the vertical direction? I mean, I just gave the answer, so it's anyways in the vertical direction. Because x1 dot is minus x1 is pointing this way, and x2 dot is x1 is pointing this way. So the vector sum would actually be pointed this way, right? Over here, correct? Everyone with me? Any doubts? Hello.
Yeah, could you explain it again, sir?
Okay, cool.
How the vector
Third
action works?
quadrant.
Yes. So okay, I'll just pick a point here. Okay, I'll just pick say 0 comma 1. Sorry, 1 comma 0. 1 comma 0. So what will my dynamics be here? x1 dot is minus 1, x2 dot is 1, correct?
Yes.
So x1 dot is minus 1. So x1 should move in the next instant along this direction, correct?
Yes.
and x2 dot is 1. So it will have to move in the positive direction in the next instant. It's instantaneous.
Correct.
So what is the net direction? Your basic vector algebra, the how do you add two vectors? It's the same. So it should be this direction, right?
Correct. Yeah.
So that's what. So if you look at any of the points over here, the system would move in that direction in the next instant. And similarly, if you look at any points in the left side, it should move in this direction. So you can try it out yourself, or else I'll have to plot the entire thing. Okay, got. I hope you got the x-axis one. Now let's look at what happens in the y-axis. So what happens? So x1 dot will be equal to x2, and x2 dot will be equal to minus x2. So what happens here in the same way? x1 would move this way, and x2 should move in the downward way, right? I hope everyone's with me. Hello, you can
Yeah.
unmute and yeah.
Yes. Yes. Yes.
Yes. Okay, cool. So the net direction would be this way along, on this axis. Similarly, for the down minus y-axis, it will be here. So if you plot this entire, you can pick any point and you find a vector. There are infinitely many points, so don't try. So you can use a quiver plot. So finally, you can see that all these vector fields are pointed towards this line. So why is this line so special? So when you plot it on MATLAB, you can see that all these, everything is pointed towards that line, and on that line there are no arrows. So if you plot, if you have a MATLAB, or you can just try. So what that line is actually called the equilibrium points. It's called the equilibrium. So in this case, there are infinitely many points because it's a line. So you have equilibrium as x1 dot is 0 and x2 dot is 0. Basically, there is no change in the system. It'll just be there if you leave it alone. Okay. So this is the definition of equilibrium point. Like f. Okay. So this is. So as of now, you can take this as the definition. We'll look at it later. So when all the dynamics is equal to 0. So when you equate this to 0 and solve for the right hand side, what do you get? x2 minus x1 is 0. x1 minus x2 is 0. So basically both are the same equations. So you have x1 equal to x2, right? So at these points, the dynamics is 0. So that's why you get this line here. So on this line, x minus y equal to 0, or y equal to x, or x1 equal to x2, you have equilibrium. So all the dynamics will finally converge to that straight line. So is everyone with me? Any doubts? I hope. So did you understand what the concept of equilibrium point? Hmm. Is everyone with me? Hello?
Again, based on these equilibrium points, can we conclude that the system is linear?
System is linear. No. So linearity depends on how the function is. So x dot equal to f of x in the most general case. Okay. But for linear system, f of x will have a particular form, which is a matrix times x. Okay. And you have, you just have one equilibrium point, or that is isolated, or you have a subspace of equilibrium. That's the only two case in a linear system. So this is actually a subspace. You learn what subspace is in week 2. So if you don't know. So this is actually a subspace or a line, on a plane through the zero, through the origin is a subspace. So either there will be just 0, 0 or any line passing through this origin. So linear systems, you can, if you have this form, x dot equal to ax, then it's a linear system. Or else it's, all the systems in physical reality are non-linear, and you can approximate them to linear models around a small region. So we'll see that in week 4 or week 5, I guess. So you can't conclude that it's a linear system because you might be looking at a really small. Okay, let's look at the pendulum. So for the pendulum, if you just look at here without damping, so you'll have these oscillations, right? So I hope you can try plotting the pendulum equation. But if you just look at this region, you will conclude that it's linear. But in fact, it's like non-linear. You have another equilibrium point at pi, where if it's you have multiple isolated equilibrium points. So it depends on how large or closely you look. You can approximate this to a linear system if it is really close to an equilibrium point. So I hope that clears your doubt. Okay. Good. So I hope everyone's with me. Any doubts, you can just unmute and ask. So for much complex systems, you should use MATLAB. I don't think you can hand draw. It's not intuitive to, for such simple system, it's very intuitive. Okay, now we'll look at, the how to model an epidemic. So yeah, so this would have been the, very common thing during Corona. So this is not something which has some, physical first principles by which we can model, right? So you don't have Kirchhoff laws or, Newton's laws to model these things. So it's more, just like the client web server model that in the lectures. So this type of system is called a compartmental system. So we'll look at the most general, most basic model of a epidemic. So you have a total population. Okay, say there are 100 people in a city. So you have 100 people in a city, and so these are all susceptible, or they can get, corona, for example. They can get sick and get infected. So this S represents the total number of people who can get a virus or any disease. Okay, so that is S. Then I represents the number of infected people. So there could be some infected people here. Okay, so that is I, and R represents the number of people who have recovered. So we are assuming that once you recover, you don't get a second time. So that's recovered, or in the sense it could be, people could die also. So it's like recovery or death. So R represents the number of people who have recovered. So in this model, the susceptible people get infected, and the infected people recover eventually. So there is no like recovery again. There is no this thing. So yeah. So how do you model such a thing? Like you, how can you? There is nothing like d equal to L di by dt or anything like that. So how do you model this? So basically, also one more thing, S plus I plus R will be, okay, I'm just normalizing it to 1. Okay, so S plus I plus S will be your fraction of people, I will be your fraction of people infected, and R will be your fraction of people recovered. So I'm just normalizing it to 1 for, it's easier to handle not fractions here. So how do you model this? So firstly, so we can say that intuitively, the number of people or the fraction of people uh, getting infected. So they can only get infected from here, right? So the fraction of people getting infected would depend on the number of people who are already, susceptible, and also the proportion of people who are infected, right? So it depends on how many people are infected as well as how many people can get infected. So it's because it's proportional, it's you can model it like this, right? Is everyone clear how I got this model? I'll tell you what beta is and where minus came from. So is everyone clear with the first equation?
Why do you product the SI? Actually, can we have it as a additive factor? Addition?
No, because okay, so in basic physics class you might have learned that if V is proportional, V is proportional to I and say it's not voltage, I'll just take something else. Okay, so x1 is proportional to x2 and x1 is again proportional to x3 and x1 is proportional to 1 by x4. So it's not additive, right? If it's proportional, it's multiplicative, correct?
And why do you go for a negative term there?
Huh?
Minus beta is there? Yeah.
Yes, minus sign comes because the number of people actually reduces here, right? Because everyone's going to the infected side.
Oh, you take the total population is constant, and you are saying that the vulnerable are infected,
correct,
and the recovery rate is being accordingly.
So beta is the infection rate here.
Okay.
Yes. So yeah, exactly. So the susceptible people actually, it decreases, right? Number of susceptible people. So that's why the negative sign comes. And where do these people end up? In the being infected, right? So it's the same amount of people who get infected, correct? So it will be the opposite sign in the infected dynamics, correct? Minus people would start getting, they'll start recovering. So that would be minus some gamma times the number of people who are infected. So people who are infected would, eventually recover. So that's our basic assumption. So I hope the second equation is clear.
Yes.
Cool. So now where do these recovered people, what happens to the recovery, the recovered people? It's gamma times I, correct? Because all these people would end up here, correct?
Yes, sir.
So this is your a simple, SIR model of a epidemic. And gamma is the recovery rate.
It is becoming a non-linear model. Right?
Yes. Yeah. You can tell me that. Is it a linear or a non-linear model?
It's non-linear because you have a product of two states there, S and I.
Yes. Yes, the product here. Yeah. So it's non-linear. Correct. So can you find the equilibrium point of this? How do you find the equilibrium point? S dot is 0, I dot is 0, R dot is 0. So when there is no more change happening in the system, so that's your equilibrium point. So if you equate this, S times I equal to 0, S times, so this is from the first equation, beta is a positive quantity, minus gamma times I equal to 0 and gamma times I equal to 0. So finally, we know that all of them would get, there would be no more infected people in this model, right? Because gamma is a positive quantity. So eventually all the infected people would get recovered. Correct?
Correct.
Yeah. And okay, there is one I have already mentioned this. Yeah. So cool. And and the susceptible people depends actually on the population, and recovered people would be, finally everyone recovers. That's the main point. So everyone would get infected and everyone would eventually recover. So that's what the model shows, right? S could be anything here.
Can you write down all the three equations? What will be S at equilibrium? What will be I at equilibrium? What will be R at equilibrium?
Yes, sir. So from the second equation, we can see that S could take any value, right? So S could be any value, and R also could be any value, right? Because that depends on the total population. And I often goes, I will go to 0. So that's what the dynamics works. So
You can show that plots, right?
yes, sir, I do have the plots in fact.
Okay, good. Yeah, right.
Yes. So what happens is you have a constraint here. This is called a constraint, right? Because the system, the population remains constant. So at equilibrium, it has to follow this because I will be 0. S star plus R star equal to 1. So that's how the a basic model of the epidemic. So I'll show you. So depending on what beta and gamma is, you can actually, okay, I'll show you what the dependence is. So if you look at the second equation, I dot, and you can take an I common, so that will be beta S also a gamma common. So beta by okay. So I just took this common outside. And so if you look at this carefully, if we have beta S by gamma less than 1, okay, in this case, then I dot will be less than 0, right? What does that mean? So if I dot is less than 0, then I would eventually go to 0 because it's a positive quantity. I is, it's a fraction of people, so it's always positive. So I will go to 0 if this beta S by gamma is less than 1. In the case of beta S by gamma is greater than 1, I would increase. I am not saying it will blow up, it will just increase, right? I will start increasing because I dot is positive. Correct? Okay.
Yeah.
So that basically, it translates to flattening the curve. We might have heard about flattening the curve and things like that. So that depends on your beta and gamma. So people are trying to reduce the infection rate and increase the recovery rate somehow using interventions, right? So that's how you flatten the curve. So that's how we all were trying to do, or at least right now. So yes, if this is clear enough. Yes, for this I've taken a beta, which is the infection rate, to be some 0.05 and gamma to be 0.01. So which means the infection is more compared to the recovery rate, right? So that's why there's a huge peak here. This dotted line represents the fraction of infected people. So that's why there's a huge peak here before it decays, because eventually everyone would recover. It won't keep increasing because the number of population is limited, and we have only shown that this is just unidirectional. You can't have people coming again. So that's why it decreases, but there's a huge peak, right? And in terms of S and R, so you can see that it always at the equilibrium, S star plus R star equal to 1, right? So when S approaches 1, okay, it's the other way, sorry. When R will approach 1 and S will approach 0, right? So this black is S and this red is R. So S star plus R star will be equal to 1 in this case. Okay, now let's try to flatten the curve by taking beta as a smaller value compared to gamma. So what happens is the recovery is faster than the infection. So what happens is you see the peak has decreased, the peak, so basically we have flattened the curve because of changing the recovery and the infection rates. So that's exactly how it's an intuitive way to model a pandemic, right? So if it's clear, so I hope it's clear. So you can run these simulations. You just need to know how to run ODE solvers on MATLAB. So if you have any doubts running, you can post on the discussion forum how to run ODE solvers. So these are all ordinary differential equations which MATLAB can handle easily. So you can just run these and plot, and maybe post on the discussion forums, if you can. So.
And if you also have specific questions which you want to discuss in this live session, please post on the forum. It could be problems, it could be anything. So so feel free to post questions and feel free to attend. If you have any suggestions, any particular thing that you want to learn, please let us know.
Yes.
So how many here are PhD students, or can maybe quickly? Maybe Karthik did all the introduction anyways, but can we have a quick round of intro at least for my own this one? Can we start with Shashikant?
Sir, I am a BTech final year student
From where?
from JNTU Kakinada, Andhra Pradesh.
Okay. And why are you doing this course?
As a part of our 4-2, if we do any NPTEL courses upfront, we'll be getting a free time for the next 6 months, sir. That's why I chosen a course.
Okay, good. Next, Ananya.
Yes, sir.
Yeah, okay,
I am active first.
okay. You're from IIT Madras. Okay. Nedumal. I don't know how to say your name.
Yeah, sir. I'm working as an associate professor in a self-financing institution in Tamil Nadu.
Oh, okay, good.
See up the basics of engineering and
Okay. Who else is non-IITM here? Karnan,
Yes, sir.
you're IT or you're non-IIT?
No, sir. I am from Gandhi Ramanoran Institute, Tindigal, Tamil Nadu.
Okay, good.
I am a PhD scholar in mathematics department. Actually, we are working in a control theory.
Okay, very good. Okay,
For the basic need, I joined this course.
Okay. Yeah, so I think please attend these sessions. Maybe you can tell others also that we really want to. And then the scope of NPTEL by also have weekly interactions with journalists. Soumyadeep? Hello, please.
Hello.
Yeah, hi, Swati. Yeah,
Sir, good evening, sir.
Yes, sir.
Sir, my name is Swati, sir. I am a research scholar. Recently joined in NIT Mizoram, sir.
Okay, very good. Okay.
They are given the coursework for NPTEL courses. They are given 2 coursework, sir.
Okay.
That is control engineering and linear systems theory. So that's why I have chosen, sir.
Okay, very nice. Yeah. So I hope you'll keep attending the sessions.
Okay, sir. Definitely. Say, my aim is I want to get the NPTEL certificate, sir.
Okay. So please feel free to ask questions in the forum here. Just make it interactive. If you know some other answer of the questions in the forum, also answer that. We'll try to solve as many problems and all in this forum. Okay.
Definitely, sir. Definitely, sir.
Okay, good. Soumyadeep Das. Okay, so he's on mute. Anyway, so that's all, Karthik, for today, or you want to talk a little more?
Sir, actually, if anyone has doubts regarding the week, they said we'll do it in the end. So if anyone has, week 1 doubts, we can week 2 also maybe, but it's better to keep,
Yeah, weekly schedule we can keep.
Yeah. So anything related to week 1?
Okay, I'll be off. I'll see you guys maybe next week.
Can I ask a question?
Yeah, sure.
What version of MATLAB are you using?
The latest one you can use the
22.
I think I don't use 22. I think I use 22. Yeah.
Okay.
It updates every time, so I don't keep a track of that.
Okay.
So, yeah, any other doubts regarding the week lectures or any other?
Sir, can you brief about finite dimensional system and infinite dimensional system?
Okay, finite and infinite dimensional. Okay, so yeah, it's actually there was a math person here, right? Where I forgot his name. So,
Yeah. Karna.
Yes, you can.
The dimension related to basis. If you have finite number of bases, then it will be finite dimension. Otherwise, it will be the dimension basis. It generates the whole space. Definition says basis means it generates the whole space. If you have a number of in real number in R2, the basis number of bases is 2, therefore it is finite dimensional. If you take polynomial space, it need more number of polynomial with infinite dimension. It needs more number of bases. That is why it is infinite dimension.
Yes.
It depends
So
upon the basis time.
yeah. So what basis is actually is the minimal set of linearly independent,
and the maximum generated.
Yeah, which can generate the entire vector space. We'll look at vector space in the next week. So for the real space R1, R2, R3, you just need 1, 2, 3 bases, which are finite. But for say, like he said, the polynomial basis, you need an infinite. How do you represent a polynomial? F of x equal to x plus x square plus x cube plus etc. Right? So each of them is a basis. X square, x cube. So each of them is a basis. So you'll learn if you take a course on real analysis or functional analysis, you will come across these bases and what there are so many things like inner product spaces, vector spaces. So you have to go through all that to show what a basis is, orthonormal set of bases, things like that. So yeah, so it's not about the system, it's actually about the underlying space.
Okay.
So any other doubts, or else we can wind up this session for the day. Okay, so no other doubts, right? Cool. So yes, so yeah, see you next week, and just make sure you post questions, or you can even give answers to each other's questions in the discussion forum. So so yeah, Arjun.
Excuse me.
Yeah.
Will you send that annotated PDF?
Yes, I think the NPTEL office will post this PDF.
Okay.
Yeah.
How is this course schedule? Is it the same time as today?
Yes, Tuesdays 6 to 7. It's a doubt clearing session, and we'll solve just like this every weeks. We'll just take some doubts and clear the do some problems. It's the same every Tuesday 6 to 7. So, cool. So I think that's all, and we'll stop here. So yes, thank you everyone. Make sure you attend it, without fail. Even if you don't have any doubts, just attend. You will get some doubts here, or you can clear each other's doubts. It doesn't matter. So yep. So bye, and see you.